Hey everyone, welcome to the Weekly Space Hangout for Friday, February 19th, 2016. I'm Fraser, Cain, publisher of Universe Today, and this week we've got a ton of really cool stories. We're going to talk about, goodbye Philae, the Chinese plans to displace thousands of people for a cool radio telescope, Hubble directly measuring the rotation of a super Jupiter, hidden layer of meteorites in Antarctica. Oh, that is so cool. A new X-ray observatory taken to the sky, and visible light and gravitational waves. Apparently, gravitational waves were discovered at some point. But we've got a special guest this week, which we'll get to in a moment. But first, I'm going to say hi to Dave Dickinson.
Hey there.
And Dave, where are you?
I am at Norfolk Naval Air Station right now, and I'm stranded here for the weekend waiting for a military flight to Rota, Spain. Me and the wife. So it's not a bad place to be stranded, actually. So.
Are you going to be able to make it to the Canary Islands, or?
I might try. I noticed that that's not far away because Morocco, Gibraltar, Portugal, we want to try to check off some countries there. So
nice.
I might be able to try to make it down there.
That's those great observatories up there.
I just missed. Oh, go ahead.
Oh, go ahead. No, you just missed something.
No, I just missed being able to go to LIGO last week for the announcement, unfortunately. LIGO Livingston, had that come out a day or two prior, I probably could have made it there.
Oh, that would have been amazing.
I know.
Jolene Creighton from Futurism. Hello, Jolene.
Hi, Fraser, and everyone else here today. Hey.
I like your background.
Thank you. I have a ridiculously small apartment in New York City, so that's actually the living room, and I have a tiny desk here, and then we have like a curtain. It's actually a sheet.
Are you in a closet?
Essentially, yeah, I'm basically in a closet. So that's how I roll.
Harry Potter of science.
We've got Kimberly Cartier. Hey, Kimberly.
Hey, Fraser. Hello, viewers.
Welcome. You know what? We're gonna spend the whole episode and not talk about your alien megastructure.
Oh, you just mentioned them. Oh. So close.
The irony. We got Morgan Remberg. Hey, Morgan.
Hey, Fraser.
And our special guest, as promised, we've got Rebecca Roth from NASA Goddard. Rebecca, welcome to the Weekly Space Hangout.
Hey, great to be here. Thanks, Fraser.
This is so cool. So a big thanks to, I think, Nancy Graziano for setting up this special guest, and this is awesome. I'm super excited to talk to Rebecca. So Rebecca, why don't you let people know who you are and what you do?
Yeah, so I work at NASA's Goddard Space Flight Center, which is just outside of Washington, D.C. in Greenbelt, Maryland, and I work in the Office of Communications, as really my background is a photographer and a photo editor. And when I started here about 6.5 years ago, they didn't have anybody in their Office of Communications who was sort of focused on the imagery coming out of Goddard. And for anybody who follows us, or for anyone who follows news about NASA, there's a lot that comes out of some of the other centers, but we have a lot of Earth imagery and images of the sun and the moon and Hubble and JWST, and so there's just a lot going on here at Goddard. And so when I started 6.5 years ago, there was definitely part of the job was going to be sharing this imagery on social media. I don't think we ever anticipated how popular it was going to be. So sharing the images on places like Instagram and Flickr and Twitter and Facebook and but also places like or finding imagery for our stories that we put out for our webpage.
Yeah, and the amount of photographs that you have available to you is just a bottomless well. I imagine just decades and decades of photographs have all come through this one center. You must have hard drives filled up. Can we get a sense of just how much imagery is getting generated by NASA Goddard?
Wow, I mean that's a lot. Probably isn't the right answer, but I mean you think about all of the Earth satellites constantly sending down imagery, and and then we have SDO, which is constantly 24 hours on the sun, sending down imagery, and then we have LRO, which is mapping the moon, and that's constantly sending down images. And so, just between those three things, and then we have Hubble, of course, and then there's lots of other things. So it's just, there's a lot out there, yeah.
And so what's the process then? So, you've got SDO, you've got access to Hubble, you've got all of these different missions, you've got, even some astronauts are sending stuff back, and this is all kind of coming into the central repository, and then you've got to, stick your face into the fire hose and sort of guess, and start picking some stuff out to share to the wider public?
Yeah, well, some of it is based on whatever stories we're telling that day. I mean, so we have, just about every day we have new science stories that we're telling. And so those particular stories will have specific imagery for them already. But since we do have all of these satellites and all these missions with images coming in that are new, I just peruse. I'm just always talking to people and checking out all the mission pages and say let's see what the sun's doing today, or when you have these massive storms, hurricanes or tornadoes, those type of imagery is always really popular, so you just keep an eye on that sort of thing. But we have the Earth Observatory, which is out of NASA Goddard, and they're always putting out new images of Earth that tell all kinds of different stories, whether it's fires in Africa or volcanoes exploding and things like that. So, and it's all such a unique perspective that what we have to share, pretty much people aren't seeing other places. So part of it is sharing the images from the stories, but part of it is me going out there saying, what's really interesting, and sharing that with the public. And the thing that I think one of the reasons these images are so popular is because they're so dynamic, right? And so people love seeing this stuff, and it's sort of across the board. I mean, you don't have to be a science geek or a NASA geek or a scientist or anything like that. We've just really have seen that teenagers, kids, grandparents, adults, teachers, whatever, are interested in it. But the thing that's really nice about it is we have a whole host of science writers who I can go to and be like, hey, I have this awesome SDO image, what's going on here? And they can get back with the scientists and they can write a quick caption so that when we share it someplace like Instagram, where these aren't people who are there to look at science imagery, but they can read a caption and say, oh, that's pretty cool, I had no idea. So
I mean, when I think about all this imagery coming back, you've got all these images of Earth, you've got all these images of the Moon, all these images of the Sun, and you've got sort of the scientific data that's in there, but you don't necessarily have the context of what it is that's happening. And so I would love to sort of get a sense of how you do find this kind of stuff. I mean, I can imagine, as you said, right, as someone says, oh, there's a volcano going off right now in Italy, say, and you're like, I wonder if we have a picture of that. And what do you know? It's an amazing picture, and we didn't even realize, because all I'm sure you had was the coordinates and the date that the picture was taken, but not anywhere to say, oh, by the way, this is a phenomenal picture that really shows the the volcano going off. So I'm just wondering, do you stumble across this stuff and then appreciate it for its artistic value? How does that work out?
Yeah, I could share a pretty unique image. I mean, this one I think was taken from the International Space Station. So I don't know. Can you guys see that?
Yep, totally.
But so I mean, the way I find, I mean, there's websites you can go to, and one of the things that's really great about all these images that I share is that NASA's part of the federal government, and all these videos and anything we put out is in the public domain. And so not only is it available for people to use and reuse and share, but the places where I get these pictures and videos are public websites that anyone could do what I'm doing. Well, hopefully I bring something special to it. But I mean, the websites that I go to are the websites that are available to the public for anyone to download this imagery.
Yeah, I think it's super important to understand that, right? That the data goes to these public repositories first, and then you access them and we access them simultaneously. I can remember when the Curiosity landing happened, we were racing NASA to try and get the first pictures published out on our live stream, because they were just going to the same place. We knew where the bucket was, and we knew where
Right.
those pictures were going to show up, and we got our hands on them, literally as quickly as NASA did, and we were showing them on screen. We didn't necessarily understand what we were looking at, but we had access to the pictures. And I think another great source of this is like all those pictures from Hubble.
Yeah.
There's great, Hubble is going all the time, and all this data is just dropping into these repositories, and there's, really important science, but also these beautiful pictures. So how can people who want to dig through these mines, where can they go and look?
Well, they could, by searching for a particular mission. If you go out there and search for, like, say, NASA Goes, you can get to the website where the GOES satellite sends down images of Earth each day. And so, but you can also just go to, like, some of our social media sites. Like, what's nice about Flickr is we can, put up an image and then link back to where the image came from. So, yeah, we don't have a page anywhere where we just list all the places.
That would be kind of neat. If someone there wants some feature ideas, some place where it's just like a stream of every new piece of imagery that's been dropped into the, you can just watch the images come together and go past and pluck stuff out and think about it. Maybe it needs more, because a lot of the stuff is raw, and like some of the stuff from Hubble, it's in this very special, like, FITS data, and somebody needs to open it up and use special software to be able to see it and be able to work with it. So.
Yeah.
But you never know. So, I want to talk a bit about the sort of the public domainness of the imagery. And this, when I started Universe Today, 16 years ago, I had no idea that this was the way the images worked. And it was really, I really stumbled, luckily, into an area where there was a tremendous wealth of images that I could use for free.
Yep.
So can you explain to people sort of what the policy is on NASA imagery?
Well, like I said, so they're in the public domain, and there's not a whole lot that you can't do. We get requests all the time. Literally from around the world, people see our images, and whether it's a scientist wanting to publish it in a paper, or a book publisher wanting to put it in an educational book, or I just got an email from an artist who is doing this exhibition, using Hubble imagery, and so. All of our imagery that we put up on Flickr, has a link to the U.S. or NASA's image use policy. But people can pretty much, reuse them. They're free to do that.
Yeah, like, can I put this image of Hubble on a T-shirt and sell it? Yes.
Yeah.
Can I publish a book of all my favorite pictures from SDO?
Yeah.
Yeah. David's just mentioning this. There's a few exceptions you do have to be careful about, right? One is APOD.
Because a lot of those are amateur images,
Right.
but they're copyrighted. So.
Yeah.
Yeah, and that's one. And then if you're going to use the NASA logo, you have to be really careful. And if you're going to use images of any of the astronauts, you have to be careful. You can't make it look like they're endorsing anything.
Right.
But yeah, I've spent a lot of time navigating around the image use policies, but generally you can kind of do whatever you want. You want to put in your video. It's so great, and it's really generous. And I think I would love to know what impact that's had on NASA's ability to get these images out into the public and just get them out into the world. Has that?
Well, I'll tell you an interesting story that comes to mind when you mentioned that. I guess it was about a year or so ago when Gravity came out, and it was nominated for an Oscar, and I thought I should probably go see this movie. And it was right before the Oscars, and I was watching this film, and I was like, somebody literally went through the NASA archives and created this film to look like real NASA pictures of Earth and pictures of the Hubble and the whole thing. And so I went through our Flickr site, and as I was watching the movie, I created a set of like real NASA images. I could probably pull it up pretty quickly, but maybe I can share it later after the show on the YouTube link. But or you could just Google it. But yeah, it's amazing that that's pretty much what they did. I read an article later that's what it said, that the art director or the director went through and that's why it's so realistic, because it was based off of real images. That most of that was astronaut photography.
Okay, so we've got a couple of questions from the viewers. This comes from Nancy Graziano, and she wants to know if you do any image processing on any of the photos that you publish. So as a sort of skilled photo editor,
Yeah.
how much of that do you bring to zazz up the pictures?
Yeah, well, not a lot. So, I mean, it's tempting, especially on a site like Gram, and you might change the contrast or something, but we consider most of these images science imagery, and the colors are set to be a specific standard and a way that the scientists have intended, and so that sort of thing I wouldn't do very much. Yeah.
Like just tune up the white balance a bit and
exactly. Yeah. I mean, and something like on a launch photograph, like we have some really cool images from NASA Wallops is a part of Goddard, and so we release images. Here's a great. Wait, let me try and share this picture because it's so fun. Oops, sorry. Our infamous frog.
The frog, right?
All right, so this picture speaks for itself. Didn't need any Photoshop, but so sometimes in a launch photo, I might jazz it up a little bit on Instagram or something. But for the most part, no, I don't with the imagery that we put out.
So this comes from Sylvan Westby, and I'm sure you were ready for this question. Have you been approached by conspiracy theorists accusing you of faking all the NASA photos?
Oh yeah, we get. I mean, pretty much on just about any image we put up, we get comments that it was Photoshop. So you're just sort of used to that.
Yeah, it's literally the background noise. I don't even.
No, we just leave it there. I mean, people they're entitled to their opinion, and
Yeah, and when you launch a space mission and take some pictures of the Earth that are really cool, I'll tell you that you faked it.
Yeah.
No, it's so weird to me that people think, I can't even imagine when you look at the thousands and thousands and thousands of pictures that are just being dropped raw onto these NASA and shared out to the public. Who would have time to edit these and fix them?
I don't.
Let's see. Let's see if there's any more questions. Any more questions for Rebecca?
I tell you, science writers, we certainly feel it when NASA goes down for the government shutdown, because that's our big go-to for a lot of images and stuff. So it's we definitely feel the impact of that.
That was crippling.
Yes.
Yeah, it was interesting. When we had the federal shutdown, I guess that was a couple years ago now, we posted on our, across all the NASA sites, we pretty much all had the same image that said, so people knew, okay, there's not going to be anything here. I think for the longest time it was our most commented on image on Instagram. I mean, just this people on both sides of the issue, but people, it was interesting to see how people felt about it.
Yeah.
So how, NASA's doing really well with its social media. It's one of the most popular on Instagram, on Twitter, on Facebook. How has running that level of kind of social media, how do you think that's changed the organization at all?
I just saw a tweet this morning about specifically someone questioning the popularity of NASA, in movies like The Martian and, like I said, Gravity, but also across, the NASA headquarters accounts, which have, millions and millions of followers. But how popular it's become, and also Scott Kelly for the past year, how popular that has been, hugely popular, the year in space. And so someone was posing the question, is NASA going to see an increase in this year's astronaut pool of people who are applying to be astronauts? So hopefully, that's part of it. That's one of the things that I love about this job, is that I know I'm reaching parents and teachers and kids and just young people who otherwise would never be seeing this. I mean, that's what's so great about social media for us now. I mean, people weren't going to be going to nasa.gov to see all this stuff, and all of the stuff that I'm able to share never would have been there. And so, you know, inspiring young people and teaching them about things and making them realize that, you know, NASA is a place where all kinds of people can work. And so I think it is. I think, you know, I would hope that it's having a positive impact and that it's getting students and teachers more interested in space and technology.
Well, NASA announced just as this show was going live that 18,000 people had applied to be astronauts, which was more than twice the amount 10 years ago in one of their last searches. So I think you're right that it is working, and more people can see themselves being part of the space agency.
Yeah, it totally restores my faith in humanity when you see the number of people following NASA on Instagram, and you compare that to celebrities and things like that, and it's, you know, it's a contender. And so, you know, though that people's fondness for that kind of imagery, I think people underestimate, you know, how much people actually do really love science and space and exploration and things like that. And I think that too many people give it short shrift when it really should be celebrated. And I think, you know, as a person whose job it is to publicize what's happening in space and to tell stories and investigate things, I've got to say mad respect to you guys for doing our, you know, the job as well as we do, which is, you know, it just keeps setting the bar higher for us to try and keep being better journalists and being better communicators, because NASA itself, the source, is providing so much raw value. It's I have huge respect for what you guys do.
Yeah. Well, thanks. Well, I just want to say real quick, and I mean, you know, it's just I'm like so lucky to have such a fun job. I mean, it's great, and but you know, we have great fans, and so this is like one opportunity. I mean, I put out images all the time and can comment on our social media, but it's unusual for me as an individual to be able to like give a shout out to our fans and say thanks for all the follows and likes and all that kind of stuff.
So let's give people some places where they can find out more if they aren't already subscribe to every single thing that you guys do. Where can they find out more?
Yeah, they should be following us everywhere. So we're at NASA Goddard on Twitter, and then we started a Twitter feed specifically for our images and video at NASA Goddard Pics is on Twitter, and then Instagram is at NASA Goddard. Facebook, I think if you just look up, I think NASA Goddard. Same thing. So Flickr, I think if you, those are our main pages. I mean, of course, Google+. So yeah, and if you went to our homepage, I think we have a link that takes you to a page that lists all of our social media pages. And then we have specific mission accounts, like to follow Hubble. That's NASA_Hubble, and we have James Webb Space Telescope. And like SD. So yeah, if you go to the nasa.gov/Goddard, you'll get to our social media page from there that lists everything.
Fantastic.
Yeah.
Well, thank you so much for joining us on the Weekly Space Hangout today. Really appreciate it, and we look forward to more pictures.
Yeah. All right, great. Thanks for having me. A lot of fun.
All right, thanks.
Bye.
Okay, so I just want to remind everyone this is a live event, so there's a chat on the YouTube wherever you're watching this, and you can ask us some questions and make comments, and people from within the show will be chatting with you as well. So let's move on. What do I want to talk about? You know what? Morgan, let's talk about saying goodbye to Philae.
Speaking of amazing imagery, the Rosetta spacecraft from ESA captured a ton of incredible pictures as it approached Comet 67P Churyumov-Gerasimenko back in the fall of 2014. And in the middle of November, as it was just completing its final approach, it dropped a lander named Philae onto the surface of the comet. This lander was supposed to touch down, latch onto the comet, drill into its surface, make observations of the area around it, take pictures, and return this all back to Rosetta that would then relay this back to Earth. Unfortunately, the landing didn't exactly go as planned. Instead of latching into the surface with its harpoon, Philae instead bounced several times off the surface, traveling more than a kilometer before it finally came to rest, not in a nice, bright, sunny sort of field, as you would on the comet, but instead underneath some cliffs that had cast it into a deep, dark shadow. And despite this, its batteries allowed it to complete nearly its entire scientific mission in the 2 days following its final landing. And it relayed all this information back to Rosetta. But its solar panels, being in shadow, were unable to recharge its batteries. And the hope of the ESA mission controllers was that around August of last year, as the comet rounded the sun, a different part of the comet would become sunny and a different part would become covered by shadow, and that light might start to fall on the solar panels of Philae, charge it up, and it could pick up where it left off doing science. And they did actually make contact with it a couple of times over the course of last summer, but it never really charged up enough and was never really able to establish the communications that would allow for reliable ongoing science action to take place. And now that the 67P has completed its close approach to the sun and is heading back out towards the outer solar system, the light falling on the solar panels of Philae is now too weak to provide the energy needed for really any hope of communication. And that means that this week they finally declared Philae lost and will stop attempting to make contact with it for the rest of Rosetta's mission, which is scheduled to run through to the fall of this year.
So that's it. We're all done. There's no heroic rescue efforts. Philae is done.
That's right, but in a sense you can imagine that Philae is actually going to have the better ending of the two, because come, I think it's September of this year, Rosetta is going to dive and crater directly into the comet. And so Philae, on the other hand, will sit on the surface of Rosetta for likely millions of years as a remnant of our first attempt to ever land on the surface of another comet.
And it
Rosetta
could be...
will also... Oh, I was...
Go ahead, Jolene.
I was going to say Rosetta will also be there. I was just going to say Rosetta will also be there, but it will just be in lots and lots and lots of pieces.
Yeah. Many little memorials.
The ESA researchers don't like to say crash into the comet for Rosetta as much as like a slow, controlled dive into it, kind of.
Are they going to try and do a slow land? Or are they going to?
I think they're trying to get it down to like a meter a second or so, if I recall, from last time I engaged it. So it's definitely going to. And they're not going to have a way to steer or aim it toward the Earth once it hits. So,
I imagine slow is relative then, because a meter a second is
still pretty moving pretty good.
I mean, these things are made out of tinfoil and chopsticks, and so a meter per second kind of collision is sufficient to do a tremendous amount of damage.
Yeah, I remember talking to one of the researchers. They didn't like the idea of saying Rosetta's going to crash into the comet. So.
Yeah, engineers don't like crash because it suggests they didn't do it on purpose.
Yeah.
Okay, well, let's move on. We'll get through a bunch of stories today. Kimberly, let's talk about directly measuring a superJupiter's atmosphere.
So we're not so much observing the atmosphere,
we're
observing the rotation via observing the atmosphere. Very complicated, but really exciting because this is the first time that we've ever directly measured the rotation of a planet outside of our solar system. So this was something, we can indirectly measure rotation rates of some exoplanets using transits or radial velocities. A lot of times, depending on what the orbital configuration is, we can sort of infer what the rotation should be. But in this case, we were able to directly image the rotation of the planet using Hubble Space Telescope. We did this for an exoplanet called 2M1207b. It's a very catchy name. It's a planet that's about 4 times more massive than Jupiter, orbiting a very, very faint, not quite star called a brown dwarf. And it's a pretty distant system for us to be able to observe it. It's very dim. It's about 170 light years away. And what we've done is we've used the Hubble Space Telescope to observe this system over the course of about 10 hours or so, and we were able to actually see the fluctuations of light coming from this planet as it rotated about its axis. Now, because the planet and the brown dwarf are so far apart from each other, we know that we're not seeing variations based on the planet's position, but rather because of the actual variability in the planet's atmosphere itself. This is a very cloudy system, a very cloudy planet, and so we're actually seeing the weather patterns of this planet as it's rotating about its axis. This is a very exciting thing to do. Like I said, the first time we've ever directly measured the rotation of an exoplanet.
And so this is hopefully just the beginning of a whole new methodology for being able to do this. What kinds of scientific answers do you think you're going to be able to get from being able to measure the rotation rate of these planets?
Well, for one thing, for one thing, when we observe the atmospheres of some planets, either through transmission spectroscopy or thermal emission spectroscopy, we're really only seeing one half of the planet. We see the atmosphere of the planet as it appears right then, and it's a very small chunk of it. But with this type of method, because we're actually seeing the entire sphere of the planet, we can start to get an idea of maybe some weather patterns or the variability of cloudiness, which can really affect sort of what the temperature and composition of the lower layers of the atmosphere are. And we can't really see them through the clouds, but knowing how the clouds are distributed around the planet can give us a better idea of it. And
being able to measure the rotation rate of a planet in another solar system is pretty tricky work. When you think about, like astronomers aren't even really sure how long a day is on Saturn and Jupiter. They weren't able to tell just by measuring the rotation rate. They had to get to the point where they could measure the magnetic, the magnetospheres around these worlds. So this is tricky work.
This is very tricky work, and when I say we're looking at the variability of light, I'm talking less than a 2% change as the planet rotates around its axis in 10 hours. So that's an incredibly precise work.
And so could you get a sense to see if like maybe they've got like big storms? You could see like, would it have its own great red spot?
I don't think we can't see quite that much. So we're still looking more at the what we call disk integrated light. So we look at a whole circle of the planet's light, and it's all blended together. So we can't see quite as much detail to get, stripes or great red spots like that. But we do know that it's very cloudy and that the cloud cover changes around the planet. So maybe on some parts of the planet there might be rain or condensation happening, and the other part might be clear.
Yeah. Good. Well, and what we want, of course, right? We want better analysis of exoplanet atmospheres so that we can detect life. So is this technique going to help find life?
You never know. It could. Certainly not for a planet like this, which is still very, very hot, very young, and incredibly distant from its host star. But the techniques that they're developing now will be useful in the future for JWST, which can get down to more Earth-sized planets and potentially Earth-like atmospheres. And if we can really get an idea of what's happening underneath those top cloud layers, that could give us an idea of whether life could be possible.
We've got a question from Truck Captain Stumpy. What kind of resolution talk about? How clear is the pic?
Well, they were using the Wide Field Camera 3 on Hubble Space Telescope, which can usually get down to sub-arcsecond resolution, which you really need to be able to separate the planet from the brown dwarf. That being said, the entirety of the planet fits maybe on 2-3 pixels at most.
So you're really just measuring the brightness of those 2-3 pixels. Yeah. Okay.
So that's exactly why we can't see any specific details about the atmosphere like spots or stripes, because the light is blended over just a few pixels.
Right.
It's like our view of Pluto 50 years ago.
Right. That's a good analogy. Yep.
Yeah.
Okay, well, let's move on. Dave Dickinson, X-ray Observatory taking to the skies.
Yeah, Wednesday morning, the Japanese Space Agency JAXA launched the satellite formerly known pre-launch as Astro-H, X-ray Observatory. Now it's known as Hitomi. They gave it a Japanese name, which means it's the actual pupil of the eye, I guess, meaning a new eye on the universe kind of reference there. But Hitomi is the largest payload at 2.5 tons that JAXA has ever lofted into space. A lot of Canadian Space Agency, ESA, NASA have a lot of instruments on this as well. And this is joining NuSTAR and Chandra, up there as X-ray observatories, but this has the capability of observing soft and hard X-rays simultaneously all the way up into low gamma ray energies, like around 600 keV, kilo electron volts.
So for people who don't know what soft and hard, is that just the wavelength?
The wavelength, when you're talking, I believe the cutoff, I think it's down around 10 keV between the lower energy soft X-rays below 10 keV, and New Star works mostly in that range. Chandra works up into hard X-rays somewhat, but this one is going to have capability all the way across the X-ray. And what's kind of cool, talking to one of the researchers, is they can do this simultaneously with one satellite with these instruments, and they get readings from the gamma ray end as well, looking at these sources. It's in low Earth orbit, and it's got a very Hubble-like orbit. I've been trying to actually spot it the last few nights here, because it's I'm a little further north than Florida now, but Hubble you can see from Florida quite a bit because it's in a 31-degree orbit, inclination orbit. So this one, theoretically, it's about the same size. It should be visible as well. So it's going to be interesting. They're doing the 3-month commissioning phase. It's kind of with the gravitational wave announcement. It was kind of a story that kind of was more in the background, but it's kind of an interesting mission. I wrote this one up for Sky and Telescope this past week, so it's going to be one to watch definitely, and we've got a lot of X-ray eyes out there. It's kind of interesting science.
Yeah, it's sort of one of the wavelengths that you do need to get outside the Earth's atmosphere to be able to even view. You can't have a ground-based X-ray telescope.
Yeah, there's no way. And it's interesting. I have a picture here because I was trying, when I was writing the article, to wrap my brain around. See if I can screen share it here. It's not showing up on screen share. But I was trying to wrap my brain around exactly how an X-ray telescope works. They use what's called Gray's incidence optics, and it looks like a big cylinder of concentric mirrors. The focal point, the X-rays have to hit these almost at a 180-degree angle instead of hitting it at a perpendicular angle to focus it down. It looks like the layers of an onion when you look at it. It looks like a big cylinder and concentric rings down through it. But again, yeah, you can't do X-ray astronomy from the Earth because the atmosphere absorbs all that. But it's kind of a very interesting configuration how they have to have these specially coated cylindrical mirrors to operate.
Yeah, you can't just have a detector. You can't like have a lens that focuses X-rays. You've got to have almost like a funnel that they bounce down and they sort of get slightly deflected as they come down into the detector. So it's a totally different way that you actually have to be able to make these observations. Really fascinating. Good. Well, that's great. More X-rays, more better.
Oh, yeah.
Jolene, got more information on gravitational waves?
Kind of, sort of. As most people are probably, LIGO announced that they'd finally detected gravitational waves, kind of the physics breakthrough of the century. Last week we were talking about how being able to detect these waves is much like going through the world your entire life, only being able to see people and never hear them. And all of a sudden you have the ability to hear sound. Kind of the same with gravitational waves. We can detect all sorts of forms of the electromagnetic spectrums, so infrared and X-rays and gamma rays and all this stuff. In many ways, gravitational waves are another way of detecting cosmic phenomenon. Einstein proposed them about 100 years ago, I think it's actually 100 years this year, and stated that basically supermassive objects moving through the cosmos will cause ripples in space-time. And what LIGO detected was two black holes coming together. A massive interaction had an effect on space-time, causing these tiny, small ripples. So as soon as they made the detection in September, I think it was actually the next day, they called a number of different teams. One of them was working with a dark energy camera, and they pointed their cameras at the region of space. We had two different teams triangulate the location, get a general idea of where we think the gravitational waves came from. However, it was an area of space that was about 2,800 times larger than the space the moon takes up. So it's a pretty wide area that they had to search. And they were looking for signs of visible light from this interaction. So we now know that it was caused by the merger of two supermassive black holes, but this event also could have been caused by, say, two neutron stars coming together. And if two stars came together, then it's very likely that we would have seen some type of visible light that was emitted during this explosion, during this sort of coming together, which would help us better understand sort of what's going on. So they pointed their cameras there, and they didn't actually see any visible light or anything like that. But that will help us, or did help the scientists rather, constrain the potential level of brightness for future observations of gravitational waves.
So you're saying they're still not sure what object actually came together to create the gravitational wave event?
They're saying that it was two black holes. There's been accepted, gone through peer review, and been published beforehand. So obviously they couldn't publish a paper saying, hey, we detected gravitational waves and we searched for visible light, but we didn't see it, until after they already made the gravitational wave announcement. So it's kind of like putting the horse before the cart, but they had to do that because they wanted the big reveal to be gravitational waves, not gravitational waves, we didn't see any visible light.
Right.
And so, yeah.
David, you had a mention there.
Yeah, just a few days ago, LIGO India got the green light as well. Some of the hardware, when I was up at LIGO Hanford last year, they had the material there from, there was going to be a third detector in the US they never built, and now this is being reborn as LIGO India. And that having those three different geographically separated detectors might give us that ability to pinpoint where the source is coming from in the sky. It kind of gives you 3 points on an axis, kind of, to when because it passes through the Earth at the speed of light, but it hits each detector at different times. So I think it's kind of interesting that advanced LIGO, as soon as they turned it on, within a few weeks they found a detection. So that was in September. So that's kind of telling that we're reaching that sensitivity now that we need. I think that's kind of cool.
Yeah. And Truck Captain Stumpy asked if we could explain for laymen why other satellite feeds weren't interrupted by the signal. So I assume that means why this sort of gravitational wave event didn't cause chaos in all the other satellites that we have orbiting around Earth. And this detection was actually it's just a really, really tiny little thing that we detected. So it's not like a supernova occurred, nearby, and so all this energy is getting, heading towards Earth and smashing into our atmosphere. These are very, very specialized instruments, and it was only because of recent updates to the LIGO instruments that we were able to make this detection at all. So other satellites weren't impacted. We obviously didn't feel it. Everything went on fine and dandy because we're detecting something that's just amazingly, remarkably small and hard to detect.
Yeah, I mean, the thing to keep in mind is that as you walk around the house, you're generating gravitational waves around you, ripples in space-time, because your mass is moving through the house. It's just that no one could detect them, even if they were really close. It's when you need those most catastrophic events in the universe, these colliding supermassive black holes and things that are moving very, tremendous amounts of mass moving very quickly. That's when you can get even the slightest chance of like a tiny little detection. But what I love about this is just that we now have a whole new way to see the universe. As you said, we can now see these places that were previously invisible, like theoretically, what's on the other, what's within the event horizon of a black hole, what happened before the, the cosmic microwave background radiation, what happened before these places where the light can never reach, but the gravity can. And so it's the beginning of a whole new type of astronomy, assuming, LIGO India gets set up, LISA gets launched, and they perfect their techniques. So exciting. Okay, great. So let's move on. What do I want to talk about now? Okay, Morning. Let's talk about China displacing thousands of people for a radio telescope.
This is a very China thing to do, I'm afraid. China is building what will be the world's largest radio telescope, and I'm going to go ahead here and try to share a picture of it. It looks like this, and it's going to be 500 meters in diameter, half a kilometer. And that's in comparison to Arecibo, which is our largest current radio telescope. That's about 300 meters in diameter. So this is a tremendously large structure that's going to allow us to peer, in some senses, farther into the universe than we've ever been able to before at the radio wavelengths. But very similar to LIGO and gravitational waves, you have to be sure you're not polluting your detector when you're trying to make these observations. And many, many things, in fact, most things that make modern life so convenient create radio waves. Things like your cell phone, your microwave, your satellite TV, all of these things use radio waves to communicate. And so what has to happen in order to make this detector work is that you have to have an area around the telescope where there aren't a lot of radio waves being generated. And in Arecibo, they were able to accomplish that by putting it out in the middle of nowhere. At the Green Bank telescope here in West Virginia, the U.S. government accomplished that by passing a law saying you couldn't use cordless phones and cell phones and that sort of thing, Wi-Fi. Couldn't use that within an area surrounding the Green Bank telescope. But in China, their solution was basically to order the 9,100 people living in this area to leave. And as compensation, each one will be paid $1,800. And that's that. They will depopulate the area around the telescope, ensure that there's no Wi-Fi or cell phones or microwaves or anything going off to harm the detector, and they're going to be able to look farther into the universe than ever before. And I found this story particularly interesting given the large debate that's being had in the United States right now about the 30-meter telescope. And here we're worried about building a telescope on some empty, unpopulated land simply because it has cultural significance to a group of people within the United States. And rightfully so, we're sort of wringing our hands about whether this is a good or bad thing to do. But clearly that's not something that concerns the authorities in China. This isn't empty, unpopulated land with cultural significance. This is 9,000 people's homes. And they're telling them, get out, find a new place to live. There's science to do here. Yeah,
but this isn't the first time that China has done this. I mean, with the Three Gorges Dam, they
have a long history of
tens
major
of
projects.
Thousands of people. And
the difference is that a lot of those projects at least could be argued to have important benefits to a much broader swath of the Chinese population, whether it's controlling floods or generating electricity. But there's not going to be that immediate, tangible, sort of life-saving benefit to building a radio telescope. And so, in my mind at least, they're on much shakier ground for having made this decision than in some of the previous ones.
Yeah, but it's a strange thing, right? Like they make these unilateral decisions, and sometimes they can make decisions like things about air pollution, right? They're just like, that's it, nobody's allowed to air pollute anymore, and like, okay, we're done. Like in places like Canada and the States, it'd be long, drawn out, protracted legal issue. But when you live in this sort of military dictatorship / democracy, you can make those kinds of decisions, and they can be for science as well as for oppression, all kinds of things. So it's a very, as you said, it's a very weird thing to happen. Like on the one hand, like a nice big radio telescope, yay, 9,000 people forced to move for very little money, boo. But it doesn't matter what we think; it's going to happen. So.
Someone was asking why they don't just build it out in the Gobi Desert.
I mean,
that was someone in the little chat thing.
That's a good question. I would imagine it wouldn't be difficult to find a place in China in which there weren't people living. I mean, China's a country similar in size to the United States, and we have plenty of places that 9,000 people aren't living in a few square kilometers. So they must have had a particular reason for building it here, and one of those reasons, and I'm sure they had several, but one of them was that just like in Arecibo, there was a large natural depression here that made building a 500-meter structure much easier. You didn't have to basically dig a huge hole or put up an incredible amount of support structure. You could use the natural lay of the land to support your telescope, and that makes it far less expensive to construct and to maintain than it otherwise would.
So if the Gobi Desert had better depressions, then it might have worked for them. Well, let's move on. Let's talk about a hidden layer of meteorites in Antarctica. It's kind of exciting.
I always love talking about meteorites and learning about meteorites because I consider them sort of discount space travel. I mean, ideally, like with Rosetta or like with Dawn, we would love to travel to asteroids and comets and such and land on their surfaces and drill down all the way to their cores and see what these things are actually made of at various different layers. For many, many reasons, this is completely unfeasible at the moment. But luckily, we have meteorites that come from such places that give us an idea of what these asteroids and comets and other various bodies that they come from, what they're actually made of at different levels. So we collected meteorites from the moon, from Mars, from a lot of different asteroids, and it gives us a sample of what our solar system is made of, and in some cases what it looked like right when it formed. And believe it or not, we actually get quite a few meteorites here on Earth every year, even though only some of them are actually reported. We collect thousands of meteorites every year. We maybe see a handful of them actually fall to the ground because most of them are falling into the oceans, right? So we lose a lot. But that's why I'm excited about Antarctica, because Antarctica is a big old ice sheet. It's really easy to find dark, rocky things on ice. And so nearly 2/3 of all the world's meteorites, 2/3 of them have been collected from Antarctica, from just scientists going down there and searching in these meteorite zones where meteorites get collected, and we get a great sample of what the solar system is made of. Except for one thing, is that when you look at all the meteorites that have been collected from Antarctica, we're missing a good fraction of meteorites that are made of iron or stony irons compared to the fraction that we collect just from random falls around the world. And it's always been a big issue because the distribution of different types of meteorites should be constant around the world. They randomly fall, and they shouldn't prefer to not fall in Antarctica versus falling in Antarctica. So where did all of these iron and stony iron meteorites go? And the answer is probably there is a layer of them hidden under the ice. So what happens, these scientists believe, is that because these meteorites are made of iron, or a good fraction of these meteorites are made of iron, they heat up a lot easier than meteorites that are just made of stone. And when it heats up just from sunlight, it'll melt the ice around it, and they'll actually sink down into the ice at a faster rate than the ice tries to push it upwards. So in Antarctica, as opposed to everywhere else, we see all of these not iron meteorites, which usually represent perhaps the cores of larger bodies, like the asteroid 4 Vesta or Ceres, anything like that. So we're getting an undersampling of these iron meteorites because they're sinking down into the ice. So this is this hidden layer of meteorites. And it'd be really interesting to drill down. They're only maybe a meter under the ice if they're there. It'd be really interesting to drill down and try and find them to see if the sampling of these iron meteorites is the same all around the world or what's different. But at the moment, our current sampling methods for getting meteorites from Antarctica just doesn't allow such a thing. It's such a hostile environment, and to bring all this equipment down to drill to find these iron meteorites is going to be very, very difficult. And they're probably not in a nice full sheet of meteorites all underneath the continent of Antarctica, but sort of just dotted around in random places. So I would love to find them. I would.
We could send an army of detectorists to Antarctica to run their metal detectors across and see if they can find any.
It could be possible. I don't know how far these metal detectors could actually detect through the ice, though.
I don't know.
I don't know.
But also, I wonder if if you've had like times of meltings and times of ice accumulation. I wonder if you get this situation where you would actually get a layer where they all just kind of sink down, and then the climate changes, and then they're all stuck in this layer that you could get down to, and then like the KT boundary, and find it, and then just dig there and just pull meteorites out of Antarctica.
That would be very, very interesting. I would also be kind of curious to see how these meteorites will have changed after however many decades hidden under the ice. What kind of alterations there might be. Would the meteorites be rusty? That'd be interesting.
But I love this idea that you're on a you're just on a snowmobile driving around the surface of Antarctica looking for rocks on top of the snow, and the only way they could have gotten there is because they fell from the sky.
Yeah, it's pretty crazy. I mean, that's why Antarctica is such a great place to go. I mean, if you're anywhere that's not a frozen tundra and you look outside, if you see a rock, it's probably an Earth rock, unless you're in Antarctica. And then that rock is probably a space rock. And that's exciting.
Awesome. David, you got a picture to share? You're muted also. He's going to share a picture of the X-ray telescope.
Yeah, this is what the soft X-ray imager actually looks like when you're looking at it. You can see kind of the onion layers on it right there, but it's just kind of neat. I'm trying to, like I said, wrap my brain around exactly what an X-ray telescope would look like versus a normal telescope.
Yeah, really cool. Let's see, have we run through everything? We've run through all of our stories. Holy moly. So why don't we wrap things up then? Because we're at the end of our hour as well. This is great. Were there any more questions? Man, a lot of people are talking about pancakes. Do I need a new analogy? I don't know.
It might need to be hashtag.
Yeah. Or maybe it just resonated so powerfully from everyone. Budam Makar asks, what do you have to say about the asteroid or meteoroid that will come close to the Earth on March 5th?
I've seen some discussion about that. I think it's quite a range on it right now. They need more observations, but I think the closest is like 25,000 miles, just above geosynchronous orbit. I mean, not anything interesting, but nothing Earth-threatening. I think this is a Chelyabinsk-sized asteroid, though.
Yeah, we posted a story on Universe Today about it. This happens all the time, and as always, nothing to be concerned about. John S. says, I have a new aim in life. I'll make Fraser Cain crack up on camera. Stay tuned. That's pretty easy, John. That doesn't take much to make me crack up on camera. So I think you should set your bar a little higher, maybe. Richard Strassel wants to know what precautions are being taken in case of shape-shifting aliens. Jolene, what precautions do you think we should take in case of shape-shifting aliens?
I might look small, but I am surprisingly strong and feisty. So I think that I should be an ambassador who will destroy any aliens who come to shapeshift and attack us.
Right, Jolene's coming out as a shape-shifting alien here.
You know too much, Morgan.
I know too much. David Joseph Wesley asks, did Einstein's theory for gravitational waves mention if proximity to the source affected the magnitude of the waves? So I don't know if that question makes sense to anyone.
I'm going to go with yes. Basically, all phenomena fall off the farther you get away from them.
But gravity is the big one, right? It's the which one? No, gravity doesn't fall off as much as electromagnetic waves.
Well, they fall off at the same gravity gravity and electromagnetism fall off at the same rate, which is as the inverse of the square of the distance.
Right.
So, yes, you want to be farther, not closer to one of these things happening.
Paul from Astronomy NJ says that Russia is pointing missiles at an asteroid. Yeah, we actually covered this in Universe Today. Yeah. So there's they're looking to test some of their anti-ballistic missiles on asteroids. Or
I noticed that some sites they were covering it. Like I didn't get into this conversation, but a lot of sites were casting this as somehow a bad thing that could result in chaos and disaster, which I suppose if you're sending ballistic missiles up on a rocket, space is kind of hard, so I suppose if it crashes, it might be bad times wherever it crashes, but the Earth is covered mostly in water, so we'd probably be okay.
They want to target Apophis in 2029 when it comes by, so they got a while.
Richard Strassel asks, how close would you have to be to feel a gravitational wave? I mean, you don't feel them, right? Because you are part of space-time and you're getting warped with it, right?
I had a long discussion with some people about what it would feel like to be close to the event, and we really couldn't come to a conclusion. Because, sure, you're part of space, and thus you're going to get bigger and smaller as the waves passes through you, but one imagines that's probably not the most pleasant experience in the world.
It'd be kind of neat to see from a safe distance if you saw the National Science Foundation simulation they put out.
Yeah, but I just, I wondered, if you're a liquid and then in a pool and then a wave goes past and the liquid experiences what the pool experiences, can they tell? Because they're part of the ripple. I don't know. And if you got close enough to a black hole to actually experience it, you'd have other concerns on your mind.
Hopefully it's not aliens merging these for fun, like some super civilization.
Peter Yannick asks, can LIGO instrument detect the gravity of our moon and other planets? David, they have to crank up. I mean, that thing's detecting everything, right?
Everything like nuclear tests, worldwide earthquakes, the land tides from the Earth and from the sun and moon passing over. They have to account for all this. The traffic going through Baton Rouge by I-10 by LIGO Livingston, that all of that shakes the detector more than a gravitational wave would passing through it. So
a car door slamming on the facility.
Yes, you're talking about the type of motion of the arms, the lasers going down the arms of like 1,000th the diameter of a proton. So, and they're actually working on another project called Enhanced LIGO after Advanced LIGO that is in a few years that's going to be even more sensitive. So, yeah. So it's amazing they can do this at all.
Yeah, yeah. Cool. All right, well, let's wrap this up. So let's give people a chance to find out more. Dave, where do people find out more about you?
Let's see, this week I'm Master Guys with a Z on Twitter. I was active on Universe Today, Sky and Telescope, and next week we're entering into the double shadow transit season, and Jupiter's coming up for opposition, so that's going to probably be my next big push to write about that, and Mars coming to opposition, the solar eclipse coming up. We've got a lot of stuff coming up.
And I've become a big fan of your Instagram account.
Yeah, hopefully we'll be doing this from Wi-Fi willing. I'm hoping to be doing this from Spain next week. So
that sounds amazing. Jolene, where do we find out more?
At Futurism, the Futurism.com website, Futurism on Facebook, and all sorts of other social media.
And if people haven't already, in your community, they can ask some questions that I will then answer on video, right?
Yes. If you go to our Facebook page and click on photos, you'll see an Ask the Universe image, and we're taking a whole bunch of questions. So that's exciting.
Yeah, do it. Okay, Kimberly, where do people find out more?
People can follow me on Twitter at AstroKimCartier, or they can check out my website at www.kimberlycartier.org.
And Morgan.
February 29th, come say hi at the special Leap Day edition of Astronomy on Tap, Colorado. I think I'll be giving a talk entitled Not Right Doesn't Mean Wrong, about how it was not crazy once upon a time to think the Earth was flat. Otherwise, you can follow me on Twitter at Morgan Renberg or visit morganrenberg.com.
But it's crazy now, right?
Yes. No, now, very different. But at one time, thinking the Earth was flat was actually a great leap of understanding.
All right. Of course, I'm Fraser Cain, publisher of Universe Today. We've got lots of great content on Universe Today. You can follow me on Twitter. And if you haven't already, we did a great collaboration with Paul Matt Sutter from Ask a Spaceman, and we did a 2-part episode about whether or not we're living in a black hole and what's the difference between the Big Bang singularity and a black hole. So it's super interesting. You should definitely come and watch it on this channel if you haven't already seen it. All right, well, thanks everyone for watching. A big thank you, as always, to the WSH crew, the Weekly Space Hangout crew. These are the fans / producers of this show. And just do a search for WSH crew, and you will be able to find out more information about them. And you can join in their shenanigans. My father just joined their crew, so you can chat with them about the show and help sort of pick topics for future shows and help suggest guests that you want to see here. All the guests that you see showing up here on the show now are recommendations from the crew, so we couldn't have a better partner in this. All right, so thanks everyone, and we'll see you all next week.